Hey there, so in this video I'm going to be showing you how power series are used in Cal 3. So this is the list of different power series that you're going to be using for you're going to be varying these to find different power series for different functions. And without having to do the whole Maclaurin or Taylor series work like you did in Cal 2. So the first one we have is 1 over 1 minus x. This is the most basic power series you can get. And it's just simply going to be x at the end. You're going to have e to the x, which is going to be x to the n over n factorial. Sine x, which is going to be negative 1 to the n times x to the 2n plus 1 over 2n plus 1 factorial. Cos x is going to be negative 1 to the n x to the 2n over 2n factorial. Tan inverse of x, which is just going to be negative 1 to the n x to the 2n plus 1 over 2n plus 1. And then you're going to have ln of n plus 1. That's going to start at 1. All the rest start at 0, but ln of 1 is 0. So that's why we got to start at 1. Actually, no. Ln of 0, sorry, it gives you negative infinity. So then that's why you need to start it at 1. Okay, so now we're going to have ln of n of 1 plus x. That's going to start at 1. And then you're going to have negative 1 to the n plus 1 multiplied by x to the n over n. So in this video, I'm going to be deriving actually tan of x, its power series, by using known power series of varying this most basic power series. And I'll be doing that by integrating one of the power series I derived from this one. So in this video, I'll be showing you how to do integration and all kinds of other things with power series. So the first example we're going to be looking at is for tan inverse of x squared. So pretty much finding this would be possible, but sometimes it's very, very difficult to do. So that's why you can use your Cal 3 knowledge of just varying known power series to get a pretty quick way of finding power series. So let's say for tan inverse of x, I know the power series is this, and it has a radius of convergence of 1. And the interval convergence is like that. So the absolute value of x is larger than 1. So x is between negative 1 and 1. So what I can do to find the power series of tan inverse of x squared is I can just plug in my x squared as my x for my tan inverse power series. So once I multiply the 2 of my x squared, I'll get x to the 4n plus 2. And then that is simply my power series for tan inverse of x squared. So it's pretty straightforward in this example, and overall it is generally pretty straightforward. You just need to be careful when plugging in or multiplying your different variables. So generally whenever they ask these questions, they also want to know what is the radius of convergence of this new power series. So that's what I did right here on the right. So you saw here I plugged in at my old x as x squared. So that's what I put in the absolute values. And then what I did is I just got rid of the x squared by taking the absolute value. And once again, I get the same radius of convergence. So then, because I have the same interval convergence, that means I will have the same radius of convergence, which will once again also be 1. So let's move on to a little bit of a harder example. So now I have my f of x is now equal to x times the cosine of a half x squared. So my known power series for cosine is this. It has a radius convergence of infinity. So the first thing I'll do is I'll just plug in my old x for 1/2 x squared. And then, so that's what I did right there. So now I'll have a half to the 2n. But technically up there I should have a 1 to the 2n, but you don't really care about a 1 to the 2n because it's just going to be a 1. So that's why I just have the 2 to the 2n down there. And I have my x squared multiplied by 2 to the n. So now that's where I'll just get, well, not multiplied, but the square of the x squared is multiplied by 2 to the n. So that's how I'll get x to the 4n. And that's my first part of my power series. You see like right there. Now we're just going to multiply what I got for my power series for cos to the half x squared by x. And that's what I did right here. So all that I did is I just added 1 to what I had right here, because like I did on the work right here, all this is multiplied by x. So when two things are multiplied, you add their exponents. They're not sort of like right here where the exponents are going to be multiplied. So that's where I'd get that. But in this case, just you have x times x to the something. That's when they're going to be added. Not, let's say here the 2 to the n is applied to everything. So that's the main idea for this power series right here. So next, we're going to be moving to deriving power series, because once again, sometimes we don't always want to be doing the work like we did before of sort of varying known power series by just plugging in stuff, because sometimes it can be very difficult. So now you can do derivatives or integrals of power series, and you can very simply get some answers. So let's say that f of x is 1 over 1 minus x. That's a known power series we have, and it's the most basic power series, and you know that its power series is going to be x to the n. And you get this, all the power series you're pretty much going to be doing are always going to be bases of this or variations of this. So this is the simplest power series you pretty much get. So we can realize that, oh, let's say I want to find the power series for 1 over 1 minus x all squared. Well, then I can realize that, oh, wait, that's actually, this derivative is this power series I want to look for. So all that I can do to find the power series of 1 over 1 minus x squared is I can just derive my power series for 1 over 1 minus x, and then I'll just get my answer. Pretty straightforward. That's the main idea. You just got to derive what you had right there by realizing that, oh, this is a derivative of that. And then, because I know this, I can just derive this to get that. That's the main idea. So whenever you're doing a derivative for power series, in this specific case, you can see that like now I'm starting my sum at 1. I did that because if not, if I started my n at 0 when I'm just deriving it, I would get 0 as my power series. So that doesn't really make sense. So that's why I started at 1. But you can rewrite this power series at 0 by adding a term, because when you're starting at 1, you're losing that term of the 0. So that's why I can rewrite it as a 0, or I can leave it as 1. So my n can be n is equal to 0, like this, and then I would have n plus 1 everywhere. That's why you have n plus 1 here, and then just an n. And then here, I'm just gonna, well, that was my n plus 1. So there's different ways to write the same power series by varying the amount of terms you have by your different starting points. Next, we can move to integrating power series. So let's say I had the function tan inverse of x, which is once again a known power series. And you can once again realize that, oh, let's say I'm trying to find the power series for tan inverse of x, but I had this power series 1 over 1 plus x squared, because this is much simpler to find than having to do tan inverse. Because let's say like this is one of the ones that you need to know by heart because you use it very often. But let's say you're in an exam and you forgot how to do it, but then you're like, oh, that's very simple because all I need to do is like I did in the first part of the video, which is just like plug in stuff from the basic power series of 1 over 1 minus x. So let's say I have the power series 1 over 1 minus x. It's just x to the n. I can realize that here I have a positive, but here I don't. So to get a positive, I can just do minus minus, which will give me a plus right there. And then by putting the negative x, I'll plug in the negative x for my old x value. And then the negative x to the n, well, this technically gives you negative 1 to the n and x to the n. And that's what you get for that first part. And then now what I can do is, but I want an x squared, but I only have an x right there. So I can square that x, and I'll get that. And then if I replace my x, my old x, by x squared, I'll get that. And then here the exponent's going to be multiplied, so that's why I'll get x to the 2n. And that's my power series for 1 over 1 plus x. But that's not what I was looking for my final answer. I was looking for the power series of tan inverse of x. So then that's why. But I know the tan inverse of x is the integral of 1 over 1 plus x. So what I can do is I can integrate my power series that I found for 1 over 1 plus x, and then I will get this as an answer. And this is an indefinite integral, so that's you're going to have a plus c. But you can plug in x is equal to 0, so tan will go to 0, and your power series will go to 0. So that's where you get c is equal to 0. So in your power series for tan inverse of x is just negative 1 to the n multiplied by x to the 2n plus 1 divided by 2n plus 1. And that's the main idea for integrating and integrating and deriving power series. Next, we're going to move on to multiplying power series. So let's say we had this question that's asking us, let's find the power series of arctan of x squared. So what is arctan of x squared? Which is arctan x multiplied by arctan x. So I'll have the power series for arctan x, which we found previously, and I'll multiply once again by arctan x. But then when it's in sigma notation, it's not really, like, it's hard to multiply the different elements of it, so that's why I wrote it as a series of terms. So if you plug in n is equal to 0, n is equal to 1, 2, 3, you get this. Same thing for obviously, that's the exact same thing. So then I'm going to multiply these different entries. So what I'm going to be doing is I'm going to be multiplying each of my bottom entries by each part of the top, and then I'll keep moving down my bottom row. So generally for these questions, they're going to be asking you to find the first three terms or first couple terms of this power series they're asking you for. So in this case, it was asking for the first three terms of arctan of x squared. So that's why I'm pretty much just going to be stopping at the powers of x squared, x4, and x6. Because the ones after, they're fourth, fifth, and sixth terms, and etc. So how I got the x squared is I did x times x, I got x squared. Then I did x times x cubed over 3, I got x4 over 3. Then I multiplied x by x5 over 5, I got x6 over 5. And I multiplied x by x7 over 7, that's why I got x8 over 7. Now we're going to move on to the second term, which of my bottom line, which is going to be x cubed over 3 times x. That's where the x4 comes from. X cubed over 3 times that. Same thing. Same thing. And then for the rest, we can just stop because that's going to be our fourth and fifth terms, and we don't really need those. So then once again, we're going to move to our third one, and then it's going to be x5 over 5 times x. And then that's going to be our little box I made of our first three terms. And you can tell that I sort of did, like, I kept moving on 0, 0, 0, because you can tell, like, you don't really need to put the zeros. I just put them there so my lines would be nice. They wouldn't be all crooked. But pretty much, you can see that there's no way you can get a power series, an answer of x squared here, because x cubed is a power already higher. So then that's why I just shifted it, just to show that there's no way you're going to get an x squared power there, or an x cubed 4 power here, or an x8 power here. I just did that. You need to put them there, but I just put them there to make it nicer and to show that there's no way to get these values multiplying. So then you can see that my first three terms are going to be x squared to something multiplied by x squared, something multiplied by x4, and something multiplied by x6. But you can see how I have x squared plus nothing, so that's just going to be x squared. I'm going to have negative x4 over 3 minus negative 4x x4 over 3, so I'm going to get 2/3 x4. And then I'm going to get x6 over 5 plus x9 over 9 plus x6 over 5. And that's actually supposed to be an x6. That's a typo. But that's supposed to be an x6 over 9. So let me just fix that right there. So that's supposed to be an x6. So there we go. So like I was saying, you're just going to be adding these x6 terms together, and then in the end, you're going to be getting 23 over 45 x6. And that is your first three terms of your arctan x squared power series. So this whole power series is for arctan x all squared. And that's pretty much the idea for multiplying. So it's similar to when you learn multiplication when you were little, but now you're doing power series. And this allows you to find the first three terms. And that's the main idea for multiplication. Okay, so now we're going to move on to division of power series. So let's say I had some question that was asking me to find the first three terms of tan x's power series. Well, tan x is equal to sine x over cos x. So what we can do is we can divide sine's power series divided by cos's power series, and that'll give us tan's power series. So with the sigma notation, I can't really do anything. I can't just start canceling terms because that's not how, because the sigma represents the sum, and you can't really start canceling different elements of a sum. So, but I can write the sigma as a series of terms like this. So this is, the top one is sine once again, and the bottom one is cos's. And this isn't a really simple division, so what I need to do is I need to do long division. So I'm going to be doing it the way I learned, which is in the way it's taught in French schools, and then I'll show you the equivalent for the English method of doing it. So this right here is sine. That's going to be my top part of my fraction right here. And then this is going to be my bottom part, so what I'm dividing by. And then this is sort of going to be my result of my first three terms of my power series. So what element do I need to multiply 1 to get x? I need to multiply by x. So I multiplied x by 1 by x squared over 2 and x4 over 24. And then I got these different elements. I subtracted them. I was left with 1/3 x3 and negative 1/3 30. 1 over 30 x5. Then I moved on. Okay, what do I need to multiply 1 to get 1/3 x cubed? I need to multiply by 1/3 x cubed. That's what I did. Once again, I multiplied every single term right here by 1/3 x cubed. I got this. I subtracted once again. And then I was left with 2 over 15 x5. And I already had two terms, so I'm like, okay, I need one more term, and to do that, I need to subtract once again. So if I have 2 over 15x5, what do I need to multiply 1 by to get that? Well, I need to multiply 1 by 2 over 15x5. And then there we go. And then I don't really care. I did the subtraction, and then I don't really care about the rest after, because all that it was asking me was for my first 3 terms of my tan x power series, and that's what I have right there. And that's the main idea for division of power series. So now I'm going to be talking about the equivalence between what I did for the French method and the English method. So for the French method, like you saw right here, I put my top part of the fraction right here, and then I put the bottom part of my fraction right here. Well, comparable to the English method, for the English method, what they did is they put their top part of the fraction here and their bottom part of the fraction here, and then what they get as their first 3 terms was right there. So it's very similar once again, because it's just the order and the different lines that really changes, and just the placement of different elements. That's the only thing that changes, but it's the main idea for both. So now the final part of this video I'm going to be looking over is limits of power series. So let's add this limit right here of 1 minus cos x divided by 1 plus x minus e to the x. So you might be thinking, oh, I could probably do L'Hopital's rule, because once I plug in, I get 0, 0, and that's undefined, and then that's one of the conditions where you can use L'Hopital's rule. But you really don't want to do that, because it complicates very, very quickly. So power series can allow you to do limits in a simpler way without having to do L'Hopital's rule, and for it sometimes to get really, really complicated and just it's not really going anywhere. So what I can do is I can write the power series for cos x and the power series for e to the x, and then once again, like in the previous part of this video where I was doing division, like this doesn't really tell you much with the sigma notation. So then that's why if I write it as a sequence of terms, I get a lot more information. So you can see that for cosine I get this series, and for e to the x I get all this, because you see how like here I'm skipping the x cubed, the x5, but here I'm keeping all of them. So because I ultimately want to get x6's on top and bottom, because then I ultimately want to maybe cancel them out or for them to all go to 0. So I want to get the same thing on top and the bottom as most as I can. So the 1's will cancel and on the top, and then on the bottom the 1's will also cancel and the x's will cancel. So I'll be left with x squared minus x4 over 4 factorial plus x6 over 6 factorial, negative x squared over 2, negative x cubed over 3 factorial, negative x4 over 4 factorial, all the way to x6 over 6 factorial. And you can see that, like for normal limits, you want to try to get a number as an answer. So you can see that the lowest common not really denominator, but the lowest common power between the top and the bottom is x squared. So I'm going to divide top and bottom by x squared. Then I'll be left with a half minus x squared over 4 factorial plus x4 over 6 factorial on the top, and then on the bottom I'll be left with negative a half, negative x over 3 factorial, negative x squared over 4 factorial, all the way to x4 over 6 factorial. And you can see that now this is the simplest form I can get, because I can actually get an answer out of it. It won't be undefined anymore like it was at the beginning. Because if I plug in x equal to 0, that'll go to 0, that'll go to 0, that will go to 0, that will go to 0, that will go to 0, and that will go to 0. So I'll be left with a half over negative a half, which is equal to, so when you have a division of fractions, this will be equal to the multiplication of the reciprocal of this. So then this will just be a half multiplied by the reciprocal of negative a half, which is just negative 2. The 2's can cancel, so I'll be left with negative 1. And that's the main idea for multiplying, and that's the main idea for using power series to calculate limits that would be much more complicated otherwise. Thank you guys for watching. I hope this helps. If you guys have any questions, don't hesitate to leave them in the description. Thank you guys for watching. I'll see you guys in the next video.